Hey everybody, this is Mrs. Belong. In this video, we're going to go over some practice problems for water potential. Now, you all have the Appendix A info and will have this available when you are doing these practice problems. So all of the values here you will have access to. So you don't have to memorize them, although as you go through these problems, you probably will memorize them just because you're doing them over and over again. So quick checklist. If you want to be successful with solving water potential problems, the big thing to do is to make sure that you are always calculating the beaker's water potential, okay, and the cell's water potential separately. The values do not mix, okay? They're not interchangeable. The only way that they really relate to each other is when you're talking about the direction that water is going to move. So the beaker's values are going to be very different than the cell's values, okay? And you don't use one for the other. Don't forget the negative, okay? And always double check your math just to make sure that you didn't make a simple calculator error. Let's try the very first problem here, okay? For these water potential problems, I want to know what direction the water is going to flow for all of them. So here is the scenario, okay? We have a beaker that has 1 molar sucrose at 10 degrees Celsius, okay? So the water potential for the beaker, okay, I'll just call it water potential B here, is going to be equal to the pressure potential we know plus the solute potential, okay? But because the pressure potential for every open container beaker is going to be 0, the water potential for the beaker is going to be just equal to the solute potential, which we know as the negative ionization constant. So for sucrose, that's 1. Times C, which is the concentration, so 1 molar, times R, which is our constant. Okay, bar, liter, mole, Kelvin. I'm not going to write it out here because then I'll run out of room. And then our degrees in Kelvin. Okay, so 273 plus Celsius is your degrees in Kelvin. So we're going to be at 283 Kelvin. Okay, so our water potential for our beaker then, water potential B, is then negative 23.51 bars. Okay, so sorry, our constant, I'll write it up here. I kept running out of room as I was doing this earlier. 0.0831 bar, liter, mole, Kelvin, okay? So we cancel out all of the different values. Moles cancel out. See, there's moles, okay? This is moles per liter here. Liters cancels out under the molar there, and moles per liter. You have Kelvin that cancels out, okay? So you're left with the units of bars, okay? So that's our pressure value here, negative 23.51 for the beaker. So for the cell, we know that the cell's water potential, so I'll just do water potential for C, for cell, is equal to the pressure potential plus the solute potential as well. We know that the pressure potential is negative 2.5 bars for the cell, so, positive 2.5 bars. So 2.5 bars, okay, plus the solute potential. So we have to calculate that for the cell. The cell has a different concentration of sucrose. So plus, let's see here, the negative ionization constant, which for sucrose is 1. It only forms 1 molecule when it goes into water. So sucrose is 1. The molarity, which is 0.8 molars, which is moles per liter. Okay, moles, sorry. Moles per liter, 0.8 moles per liter times the constant, 0.0831 bar, liter, mole, Kelvin, times the temperature in Kelvin, which is 283 Kelvin. Okay, so our water potential for our cell then is equal to negative 16.31 bars. Okay, so what direction is our water going to go? Well, it's going to go from the high water potential value, which the higher value here is the cell, to our beaker. Beaker, there we go. Okay, so for our problem 2, we have our beaker. So let's not forget here what we're talking about here. We've got our beaker, okay, that is open, and then the cell. So our water potential for our beaker here is equal to the pressure potential, which is 0 for an open beaker, plus the solute potential for the stuff in the beaker, okay? So our solute potential is equal to the negative ICRT, so negative. Ionization constant is 1, concentration is 1 molar. Okay, the R value, of course, 831 bar liter mole Kelvin, times our temperature in Kelvin, which is equal to 291 Kelvin. Okay, so our water potential for our beaker then is equal to negative 24.18 bars. All right, so our cell then, our water potential for our cell, is equal to the pressure potential plus our solute potential. So the pressure potential we know is listed here. It's 2.7 bars. So 2.7 bars, okay, plus the solute potential, which is the negative ionization constant, which for NaCl is 2, because sodium chloride forms 2 ions when you put it in water, a sodium ion and a chloride ion. Okay, so negative 2 times the molarity, or our concentration, which is 1 molar, times our value, 31 here, times our temperature, which is the same for the cell and the beaker because they are together. Okay, so that is the values here, and when we do the math for our cell, we get the cell's water potential to be negative 45.66 bars. All right, so that ionization constant really changes things up. So water is always going to flow from a higher value to a lower value, so the water in this case is going to flow from the beaker to the cell, okay, because the beaker has the higher value. So that is the direction that our water is going to flow. In our third problem here, we have a cell that is at 20 degrees Celsius, okay, containing 0.25 molar sodium chloride. It's at equilibrium with its surroundings. So when water is at equilibrium, meaning that no net flow is going in either direction, we know that the water potential values for the beaker are equal to the water potential value for the cell. Okay, so the actual numerical value is the same. It does not mean that the molarities are the same. It doesn't mean that anything else is the same other than these actual values. So the numerical values are equal. Okay, so let's see what we can figure out. Okay, we want to know what the cell's pressure potential is. Okay, so first let's calculate our beaker's water potential, okay, because we have everything to do that. So the water potential for the beaker is the pressure potential for the beaker plus the solute potential. Pressure potential is 0, okay, because it's an open container and we're on a mountain, apparently. Okay, so the solute potential for our beaker is the negative ionization constant for glucose is 1, okay, for our beaker it's glucose, times the molarity, which is 1 molar, okay, times our constant, which is 0.0831, times the temperature, 20 degrees Celsius, so 293 Kelvin, okay. So our water potential for our beaker is equal to then negative 24.35, okay. So that is also, because that's our beaker water potential, we know then that negative 24.35 bars, sorry, here we go, our units. We know that this is the water potential for the beaker, so that must also be the water potential for the cell. So now we can go on to solve the cell's water potential, or the cell's pressure potential, okay? So for the cell, I'm going to do this. I'm going to set the water potential equal to negative 24.35 bars, because we know that to be true, okay? And we want to figure out the cell's pressure potential. So the pressure potential is what we're trying to solve. The cell's water potential is equal to the pressure potential plus the solute potential. So let's figure out what the solute potential is for the cell. It's the negative ionization constant. So for the cell, it has 0.25 molar sodium chloride, okay? So for the ionization constant for sodium chloride is 2, okay? The molarity is 0.25. Our R value, 0.831 bar liter mole Kelvin, and the temperature is 293. Oh, I'm running out of room. There we go, Kelvin. Okay, oh, you can't see it. Okay, so what we can do then is, okay, so negative 24.35 bars is equal to the pressure potential here, plus negative 12.17, okay, bars if we round here to the hundredths. All right, so our actual value for our pressure potential when we use a little algebra here, so our pressure potential, we're just going to add 12.7 bars to both sides, and we get the answer of, negative, oh weird, 12.18 bars. Okay, so that's got to be the pressure potential for our cell. Okay, for this problem here, we have a cell and a beaker in equilibrium again. So we know for sure that their water potentials are equal to each other. Let's calculate the water potential for the beaker first. It's the negative ionization constant of the stuff inside the beaker, which is sodium chloride, so that's 2, times the molarity, which is this, okay, times our R value, which is 0.0831, times our temperature, which is 300 Kelvin. Okay, so our water potential for our beaker is equal to then negative 9.97 bars. Okay, because we know that the cell and the beaker are in equilibrium, we know then that this value right here is equal to the water potential for the cell. So let's calculate the water potential for our cells. The water potential for our cell is going to be equal to the pressure potential for the cell plus the solute potential for the cell. So we know a couple of these values. Let's solve for the molar concentration of sucrose inside the cell. Okay, so let's set the water potential for the cell equal to the water potential for the beaker, so negative 9.97 bars. We know that the pressure potential is equal to 1.35 bars. Okay. We know that the solute potential is equal to the negative ICRT, so negative ionization constant of sucrose is 1. We're trying to solve for C, so we'll leave that value there like so. Times our R value, 831, times our temperature, which is 300. Okay. So then when we go to, sorry about the lack of units in there, when we go to solve, we want to subtract the 1.35 bars from both sides. Okay, so 1.35 bars. All right, and then I'm going to move this up a little because I'm running out of room. Leave that like that. Okay, so then we get this value here, which is negative 11.32 bars. Okay, equal to, and then when we combine these values over here, we could say C times negative 24.93. Okay. Then in order to solve for C, all we have to do is divide both sides by negative 24.93. Negative 24.93. And we get our answer, which is 4, so our C value then is equal to 0.45 moles per liter. So moles per liter, molar. Okay, so that's our concentration of sucrose inside the cell. Okay, last problem. Again, we have a beaker and a cell that are both at equilibrium. So we know that the beaker's water potential is equal to the water potential of our cell. Okay, let's look at what we have here. Our cell, for the water potential for our cell, we have the pressure potential, which is what we're going to try to solve for, okay, plus our solute potential, which we're being told is negative 4.6 bars. Okay, we're also told that the beaker, okay, which we know is the pressure potential plus the solute potential, so our beaker, its solute potential is equal to negative 3.0 bars. Because the pressure potential is 0 for the beaker always, we know that the water potential of the beaker is equal to negative 3 bars. And because the beaker's water potential has to be equal to the cell's water potential, this problem is very simple. All we have to do here is sub out some values. So let's set the cell's water potential. So we need to figure out for the cell, okay, the pressure potential. So let's set the cell's water potential equal to negative 3.0 bars. Okay, is equal to the water or pressure potential for that, plus the negative 4.6 bars. And you could just say minus 4.6 bars because it's negative. But let's add then 4.6 bars to both sides. Okay, and then let me move this up here. The pressure potential then is going to be equal to 1.6 bars. Woohoo. So this type of problem is really just doing a little algebra, fairly simple. I hope that this helped you. If you have any questions, please come see me. Thanks.